Hi everyone, welcome to lesson 4.5, where we're going to talk about solving nonlinear systems of equations. So the methods for solving systems of linear equations can also be used to solve systems of nonlinear equations. A system of nonlinear equations is a system in which at least one of the equations is nonlinear. So when a nonlinear consists of a linear equation and a quadratic equation, the graphs can intersect at 0, 1, or 2 points. The system can have solutions like the situations below. We can have my quadratic function, which is a parabola, and a linear function, and we can have the situation where they don't cross each other at all, in which case we would have 0 solutions. We can have the situation where the parabola just touches the linear function at 1 point, in which case there's only one solution for the system. And then, of course, we can have a parabola that crosses the linear function at 2 points, in which case there's two solutions for this system. So what I'd like you to do for the first part of this lesson is go ahead and use a graphing tool. I prefer Desmos. You're going to graph the two equations or two functions that are given. So one is quadratic and one is linear. So what you should see on your graphing tool is you have a parabola and a line. Once you graph it, if you could put in a picture or a screenshot of the system here in this section. And then on the graphing tool, go ahead and trace or try to determine what the points of intersection are. And you're going to write them here. Is there 0 solutions? Is there 1 solution? Is there 2 solutions? And remember, every solution is 1 point. So each of those solutions have to have an x and a y coordinate. Next, once you get that x and that y coordinate, I want you to go back and plug this into either the linear or the quadratic function, the original ones, and then check to see if you're correct. So I gave you 2 of these examples to try using Desmos. So for B, we have the similar situation where we have a different quadratic that's given, and we have a different linear. So again, graph it, see if you can upload a picture into this section. And then once you have your x and y coordinates, if there is an intersection point, check your coordinates in either one of the original functions to see if they work. All right, let's move on to the next page. Well, of course, we can also solve nonlinear systems algebraically. So nonlinear systems can be solved algebraically using either substitution or elimination, and we took a look at that in our first unit of this course. So how would I solve the system either by substitution or elimination? Well, let's take a look at the first one that's given. It's given in the form y equals x squared plus x minus 1. It also gives you a linear function of y equals negative 2x plus 3. So since both functions are solved for y, it makes sense that we should be able to equate them, meaning we can write x squared plus x minus 1 should be equal to negative 2x plus 3. So here in this situation, again, when we solve for a system, we want to make one side equal 0. So I'm going to go ahead and I'm going to move the negative 2x over, and I'm going to move positive 3 over. Don't forget to change your signs. So we'll have x squared plus x plus 2x, so we'll have 3 x's now, and negative 1 minus 3 as it comes over is negative 4. And on the right side, then, I would have 0. So let's take a look at what we have here. We have a quadratic function. If we wanted to try, we could, again, we have all 5 methods of solving And it looks like here that we might be able to factor. Can we come up with two numbers that multiply to give me -4 and add to give me 3? We could have -1 and 4, but that doesn't, that adds to 3. So now that we have both of those, we have x minus 1 and x plus 4, and that's factored form. So then by the zero property rule, we can take x minus 1, the first factor, set that equal to 0, and we get x equals 1. And we can take the second factor, which is x plus 4, set that equal to 0, and when I simplify here, I get x equals -4. So we have two x solutions, two possibilities for x, but we still need to find y. So let's go back and we can plug both of these in. And I'm going to use the linear function just because it's a little easier. We don't have to deal with that squared. So y is equal to -2 times 1 plus 3. So for the first x value, my y is going to also come out to 1. And so for the second x value, I'll plug that into the same linear equation. So -2 times -4 plus 3. And y in this case is going to be equal to 8 plus 3 is 11. So here we have two solutions, and I'm going to write them out here. We have 1, 1, that's the first solution, and the second solution is -4, 11. Now, what I want you to do is go back and check your solutions. So again, let's pick one. Let's go with the quadratic this time and see how that works out. We're going to use the quadratic, the original quadratic function, y equals x squared plus x minus 1. And we're going to check each of our solutions to see if they work out. So the first one is 1, 1. So I will replace the y with 1. And the x is also 1, and square that, plus 1 minus 1. So 1 is equal to, these cancel, 1 squared is 1. So that first point checks out. And the next one we'll do, same with the quadratic function and the original function, x squared plus x minus 1. This time we'll substitute our second point, which was 11. -4 was the x, square that, plus -4 minus 1. 11 equals -4 squared is 16, minus 4 minus 1. So 11 equals 16 minus 4 is 12, minus 1 is 11. So we were able to use elimination and then factor the quadratic to find two solutions for our nonlinear system. Here again, let's take a look at B. My functions are set up so that y is equal to x squared minus 3x minus 2, and my linear is y equals -3x minus 8. And since they are both y, if they are a system, then they can be set equal to each other. So x squared minus 3x minus 2 equals -3x minus 8. To solve, we're going to move that -3x over, and we're also going to move that -8x over and change the signs. So I'll have x squared, -3x plus 3x, that's going to cancel out the x terms. And then -2 plus 8 is going to give me 6 equals 0. So here we have a situation. We can solve this by taking the square root. So to solve this, I'm going to go over and I'm going to move this +6 over so that I will have now x squared is equal to -6. To solve this, we would take the square root of both sides, but as we know, we can't take the square root of a negative number. So when we get to this point, we would have to just say that there are no real solutions. And this happens to be done. We have no solution, so there's nothing to check. All right, so the last one I want to do is take a look at matching the system of equations with the graphs that you have. So let's look at system number one. So in system number one, we have one quadratic function here and one linear function here. The quadratic is in standard form and the linear is in slope-intercept form. So the pieces of information that we can get from standard form of the quadratic is that its y-intercept here is equal to 1. Now, for our linear function, the y-intercept is also 1. And in this case, the slope is 1, which is the coefficient in front of the x, which is 1. So let's go to our graphs and see if we can find the graphs or the system of functions that match up. So we are looking for graphs, a parabola that has an intercept of 1. So A has a -1, B has a 1. So let's take a look at this one. Our parabola crosses the y-axis at 1, and our line crosses has an intercept of 1, so that's good. And then let's check the slope, up 1 over 1, up 1 over 1. And so since this slope looks like it is 1, then B seems to match number 1. All right, let's take a look at system number 2. We also have the quadratic in standard form, and we have the linear in slope-intercept form. And here we have the y-intercept of the parabola is going to be equal to 2. And then for the linear function, the y-intercept is going to be equal to -3. And our slope here is -1. So let's go ahead and take a look at the graphs and see which ones match. We are looking for a parabola that crosses the y-axis at 2. So C does not. There's the graph on one other side. So here we do have a parabola that crosses the y-axis at 2. And we do have a linear function that crosses the x-axis at -3. And then if we check the slope, down 1 over 1, down 1 over 1, this slope is actually also -1. This happens to be a solution or a system that's not going to have any solutions. You can see that the parabola and the line don't ever cross each other. But anyway, D seems to be the response for number 2. So let's go to system 3. So the linear system here, the linear function has a y-intercept of -1 and has a slope of +1. And then the y-intercept of the quadratic is equal to -1. So let's go back up. We'll start with A. The linear system has an intercept of -1, so that works here. It also has a slope of 1, so up 1 over 1, up 1 over 1, so this slope does look like it's +1. And then we want to check that the parabola also crosses the y-axis at -1. And so for our third system, it looks like our answer is A. So by process of elimination, obviously our fourth system must be C, but let's just double check. So the linear function has a y-intercept of 3, and we have a slope of -1, and then the y-intercept for the quadratic, or the parabola, is 5. So let's just go to C, and let's double check. So For system C, we see that the linear system does have a y-intercept at 3, and we have the parabola, and that has an intercept of 5, so that's good. And then we want to make sure that our line has a slope of -1. So down 1 over 1, down 1 over 1, and the slope here is, yes, -1. So all of that checks out, and so for our functions and systems of equations, we finished all the matching. So, all right, go back and check the other systems using your graphing tool like Desmos, and then submit that so I can take a look. All right, everyone, thanks.